Alright, welcome. In this video I want to do a quick introduction to the general data structure of a graph or a network. Basically, if no other data structure will do, then it looks like you're probably going to need a graph. So let's take a look. We'll start with just a few examples of graphs that you might already have experienced in your real world. So the first one that I think is very common these days is the idea of a social network. And actually I've got two sort of social networks displayed here. I want to start with the one on the left here. This one is a little bit hard to decipher. In fact, the lines connecting them are a little bit light on this diagram, so it might not be showing up very well. But you can see there are indeed lines between a lot of these different dots on here. Now this diagram here is actually a depiction of my Facebook friend group from circa 2013, and the reason it's so old is because you can't actually do what I did here anymore because there are more privacy protections built up. Now what I did here, and you can still do something like this, is if you go to wolframalpha.com and you type in Facebook, it will ask you if you give permission to your Facebook, and if you do, it will go and take a look at all of your Facebook posts and give you a really interesting statistical report about all of your posts and other activity on Facebook. For instance, it will make a little word cloud for you of all the words you use in your posts, telling you maybe what topics you are most likely to post about, among other things. Now, I haven't done this in a number of years, so one of the reasons I haven't done it in a number of years is because as growing privacy protections were built in, there was sort of less and less that the Wolfram Alpha algorithm was able to do. Now, what it did here, this is one thing it's not allowed to do anymore, is because I gave it permission. My friends didn't give it all permission, but at the time, because I gave it permission, it would go out and mine all of my friends list as well. So this was all my friends at the time, again about circa 2013, I believe. And then the way that they structured this graph to present it to me was two dots. So every dot on this graph is one of my friends. And two dots on this graph would be closer together if they were mutually friends, so if they were friends as well. So this little pocket down here are folks that are all also friends with one another. And again, you can maybe see that if you have, if you can see the lines there. Again, it's pretty light. But this group, where they're all sort of connected to one another, is a group of friends that are all friends with one another. So I'm going to sort of diagnose each of these little clusters here and let you know a little bit about what you can expect. Now, first of all, I have a fairly large group of friends from high school that I actually still stay in contact with, about 10 to 12 of us. And in that time, I'm old now, I'm 42. In that time, some of us have got married, we've met some of each other's siblings or cousins, we've sort of grown into a large group of friends, and so I expect that this group here, well, most of them I know, the tight group sort of in the middle are mostly all of my close friends from high school, and then everyone that sort of radiates out around here are any of our siblings or cousins and so on who have been brought into the mix, significant others and so on. And so this is a fairly large group. That's my core friends, I guess you could say. Okay, my core friends. Now, I want to jump down here. Down here, I actually have my families. My mother's side of the family. I think this is my mother's side of the family, and this is my father's side of the family. And there's sort of a lucky happenstance that two of my cousins happen to be friends just sort of randomly, and so they actually have a link, but otherwise this group here is sort of self-linked with one another. This group over here is sort of self-linked with one another. They're my other family, but there's sort of one stray link between them that keeps them connected. But my families and my friend are sort of, for the most part, separated. So I don't have too many linkages between my high school friends group and my family. Maybe my sister, although she's not on there. So that's why we don't see too many links there. But again, there is sort of the one random link connecting both sides of my family. Now, then I've got a couple other isolated groups out here. This group here, again, this is a little bit older, but this was my StarCraft 2 guild, basically. They were internet only friends for the most part, so I never really saw any of them in real life. I only saw them online, although we played online games for many years. However, how I got connected with them is through an actual friend. So this is an actual friend who I have seen in the real world. In fact, this friend is a brother of a closer friend, my high school friend. So, my friend's brother's friends became my internet guild, and here they are sort of isolated out by themselves. And then another internet community that I am a part of is also also isolated out here. Now, these folks I have met at a conference, once or twice in the past. This is sort of a smaller group corresponding to my research group. If we were able to do this today in 2020, now that I've been engaged in my research for over a decade, that group would probably be considerably larger. Then we actually have one other isolated individual out here. This individual isn't connected to anyone except me, because they're still my friend. This actually happens to be my supervisor when I was on my postdoc in Mexico City. So he doesn't know any of my friends, although he might be connected to my research group if we did this in a more modern day. And then down here we have my landlord from when I did some teaching near Toronto in Canada. And so again, that landlord doesn't know anyone else in my sphere of influence, and so is completely isolated. So this I use as sort of a nice little graph. Again, it's getting old. I wish I could still do this today, but for privacy reasons it makes sense that we couldn't. But it's a good way that we can show how data about our social network can be captured using this sort of network or graph data structure that we want to look at a little bit more. Now, speaking about Facebook, a lot of what we call network science has been done to study Facebook and other social networks. And one sort of game in the social network is see how many hops it takes to get from one person to another. So from you to a friend, of course that's only one hop, but to a friend is two, and so on. So how far can you hop before you run out of people to hop to, I guess, is one way to look at it. That's talking about the width of the network. And it turns out Facebook is fairly shallow. We can only hop maybe a handful of times before we've included everyone on Facebook. And so that's sort of an interesting, and what I mean by that is if you start it yourself, take all of your friends, take all of their friends, take all of their friends, so what's that, maybe 3 hops now, take all of their friends again, that's 4 hops, we're now getting to close to being all of Facebook. And if we do that 5 or 6 times, we've got all of Facebook for sure. So these types of questions are questions we can ask about the structure of the network or the graph that is created by the links that are formed on Facebook. Now, Facebook is one social networking site. There are obviously different ones, and these different ones allow different rules about connection. The thing about Facebook is if I want to be connected to you, I have to be your friend and you have to be my friend. It's sort of a bi-directional mutual thing. But in other social networking sites like an Instagram or a Twitter and so on, it's possible for me to follow you, but you not to follow me. In this case, we might have 2 directions on the potential connection. The other network that I have here, and I've got good old Kevin Bacon sort of hanging out down here, so mostly to highlight so you can see here that this network has Kevin Bacon in it. So is this Kevin Bacon's Facebook group? No, it's not. So this is a different kind of social network. This is called a collaboration network. This network was created to help play the game 6 Degrees of Kevin Bacon, which is sort of a silly game where you play by naming some popular actor, and then you try and name a series of actors that leads to Kevin Bacon, where you can only name actors that at some time shared a role in a movie or a TV show with the original actor. So we can jump in here. I see Christopher Plummer here, sort of a famous actor from, say, like The Sound of Music, and so you might say, okay, well, he was in The Sound of Music with Julie Andrews. Julie Andrews was so and so and so and so. Maybe Julie Andrews actually was in a movie with Kevin Bacon, and that might be how many jumps it takes you to get to Kevin Bacon. And of course, the game 6 Degrees of Kevin Bacon is the goal is, can you get there in 6 jumps? In the same way we were trying to get through jumps in Facebook to cover all of Facebook. And so this is sort of a fun game that used to be played, and then it became one that became interesting to study once we got into graph theory, and we were able to build these sort of graph networks, where basically this network is such that every node is an actor, and then every connection is formed if they have ever acted together in, again, a movie or a television show. And Kevin Bacon is chosen as the sort of target because he's a very prolific actor, and he has been in many movies, sort of like a Samuel L. Jackson or a couple other actors that you see all the time, and so that means that it's likely that we should be able to link to Kevin Bacon pretty easily. There's a whole bunch of actors who have just been in movies with Kevin Bacon himself. So this is sort of a fun pop culture game, but it's a game of basically finding paths in this graph. And if the graph was sitting right in front of you like it is here, it might be easier to find that graph. Now, one thing we notice from this graph right in front of us is that it's actually pretty hard to read, and a lot of graphs, just the visualization problem of just showing all of the different elements, in this case actors, can be pretty difficult. Okay, so this is just one collaboration graph. We could do this also with influence, but there's one other collaboration network or graph that I might want to talk about. So imagine you're actually an actor. Maybe you are an actor. I don't know. And if you are an actor, maybe you've acted with Kevin Bacon. And if you have, then we say you have a Bacon number of 1. So that's how many hops it takes until you get to Kevin Bacon. So if you're an actor and you've ever acted in any sort of formal production, something we could track in this network, then you probably have a Bacon number. And if you have a Bacon number, then you're sort of a special privileged person in the world, someone who can calculate your Bacon number. If you haven't acted before, then your Bacon number is infinity. And my Bacon number is infinity because I've never been in a formal production, still waiting for that opportunity. But I do have a different number. So once the Bacon number was sort of identified, in different fields, you could come up with similar types of numbers. And then actually, as a computer scientist and who has done a little bit of work in mathematics as well, I have published papers before with a number of researchers, and one of those researchers was my master's supervisor, John Watrous, and in the publication realm, and especially in math, we don't have a Bacon number. Kevin Bacon never published any mathematics, but there was a sort of Bacon-like mathematician named Erdos, Paul Erdos, and Paul Erdos was, like Bacon, a very prolific mathematician. He wrote papers on many different topics in the way that Kevin Bacon is in many different genres of film. And so he also had many different co-authors, and in fact, he had 509 co-authors. So if you were one of those 509 co-authors of ERDOS, your ERDOS number is 1. Well, my master's supervisor, John Watrous, he wrote a paper with another of my master, at least advisors, Richard Cleave, who wrote a paper with someone who I've forgotten now, who wrote a paper with Paul Erdos. So that means John Watrous, my master supervisor, has Erdos number 3, and Richard Cleave has Erdos number 2, and I have Erdos number 4. So I at least have an Erdos number, no Bacon number, and at least there is supposedly a small group of people who both have a Bacon and an Erdos number. And if you're one of that small privileged group, then we call that your Bacon Erdos number. And of course, now we can use this as a way to rank everyone in a new society based on Erdos numbers. Okay, that sounds a little bit crazy. Let's move on. Okay, so what other kinds of networks might we encounter? So here, the word network, social networks uses it. The word network is sort of a synonym to graph. So while we're talking about graphs here, networks is going to be just a swap out piece of jargon. And we can see here that computer networks is sort of one of the inspirations for that type of idea. Now here's sort of a more modern look at a computer network. We used to have actual wires connecting them. If you have a computer network at home, you might actually have your PC hooked up to your router, but otherwise we often connect wirelessly these days. And of course our router is connected out into the rest of the internet. And so the network itself now these days is quite vast. This is a rendering of the World Wide Web from probably about 5 or 6 years ago, if I remember correctly, a research paper at the time. And the research paper at the time was trying to map the web, if you will, and similar to the Facebook graph that we looked at just previously, this graph uses a technique to visualize the network by, again, if two nodes are connected to each other and they share connections with other nodes, then they are going to be sort of balled more closely together. So what we actually get here is in the middle of this diagram here, we have a lot of really highly connected sites that are all connected to one another. Okay, so a good example here would be, say, like Wikipedia, Google, Facebook, Twitter, Instagram. All these sites all have internal links, so they all link to themselves a lot, but they also link to each other a lot. So all of them would be really tightly bound in this center ball. And in fact, that this is a map of the whole web. So as you go, you've got those really tight sort of central internet focused sites. Then maybe out around here, these yellow ones are, again, high traffic sites, but not maybe as focused as something like a Google or an Amazon, maybe something like Sony or Fox or something like that. And then as you move out here, we're starting to get to I don't know, less popular but still fairly popular sites like maybe your university's website, maybe some other local business websites, and so on, until you get out maybe this purple ring here, or maybe your personal website that doesn't get a lot of traffic, or at this very outer maybe is sort of like the deep web where there's not really any links to it and there's not a lot of links from it. You have to kind of know where to go if you want to get there, and so those are very highly unlinked websites, and some of them look this little dot. I can't really tell, of course, but we could imagine this little dot has no connections or very few connections to anything else. And the purpose of this experiment was not just to sort of map and visualize the web, but was to test some theories about this, which is one interesting thing about networks, especially networks as they're deployed in biology, is that they can be very robust. Meaning, as I hope you can imagine, we could probably delete out some of these nodes, and the rest of the structure of the network is mostly maintained. And in fact, the purpose of this experiment at the time was to see what happens if we just go and scoop out the center then. What happens if, say, the Google, the Amazon, the Wikipedia, and so on, they all go down? And if any of you remember this from about, I think it was 2012, during the Stop Online Privacy Act, in the United States at least, this was a huge outcry by the people as well as the internet community to stop this act that was going to basically break the internet. And at the time, Google blacked out, and Wikipedia blacked out, and Facebook blacked out, and everyone turned off their websites basically for one day. Because no one could check out, their homework on Wikipedia that day, they all wrote letters to senators, and they all called their senators, and the senators voted no. But that was a real-world example of what might happen if, say, some of those main central sites went down. Well, what happens is, while the internet doesn't go down, we get frustrated, we don't get to use our Google or our Amazon, but the connection between all the other sites is still enough to maintain the internet. And what do I mean by that is even if Google went down, normal email transferring between not Google, Gmail would probably be down, but if you were not on Gmail, you could still get access your email. Just because Google went down doesn't mean the whole infrastructure of the internet is going to fail as well. So the purpose again of this experiment, where I stole this image from, was just to test the robustness of the web, see what would happen if major nodes in the web went down for extended periods of time as a result of sort of them intentionally going down or some kind of error or attack. Okay, other networks that we're used to at least engaging in are transportation networks. And depending on where you live, you might recognize some of these networks that I have here. This first one here is the London Underground map. So a fairly famous and popular subway system in the world. If you've ever been to London, then you know this is probably the easiest way to get around. At least it's the way that I've used when I've visited London. And of course, if you've ever used any kind of subway map before, then you're probably familiar with what you're looking at. The nodes on this map, the things that are connected, are the stations. That's where you can get on or off your train. And then, of course, the lines depicted here are the connections, the routes that the trains will take. And of course, on a subway map like this, London, we color the different lines so you know which line you want to go on. Of course, they usually have names, but the colors also help, to identify I'm going to use the purple line until I got here, and then I'll ride the orange one until I get to my destination. So these types of networks, transportation networks in general, are often used for, well, a couple different problems, but the standard problem is how do I get from here to there? And I often call this the Google Maps problem. So the Google Maps problem is, I'm currently here at home, I want to go to work, wherever that is, how do I drive there? Or how do I take the subway there if I'm using this particular map? So the Google Maps problem might better be applied here. This is the map of the United States. I happen to currently be a resident of the United States. I live up here in Washington. And so this map here could be used for me to say if I wanted to go drive down to California, I could use this map to plan my trip there as well. Or more precisely, I might ask Google to do that, and Google could use an algorithm and apply an algorithm to this graph, and then give me the output of that algorithm, which is the route, the path that I should take. And of course, this graph here, interestingly, is depicting, I believe, all of the capital cities in the United States. While I am a resident of the United States, I am not a citizen. I was not born here, so I'm not really familiar, but it looks to me like that these are all the capitals of the states. And this can be used to solve some challenging or interesting problems related to these types of graphs. A lot of you may be familiar with a problem called the traveling salesperson problem. And imagine you were a salesperson that needed to go to each one of these capital cities to sell your product, whatever it might be, and say you're driving to do this. then you might want to know what is the minimum distance you could travel. Say you're me, you live in Washington, starting in Olympia, and then trying to visit all of these cities, one of them at a time, and then return back to your home, say Olympia, um, without without usually duplicating any paths. So we don't want to sort of drive down to Sacramento and then back up along the same route visiting the same cities more than once. We only want to visit every city exactly once, return home, and take the minimum distance. This is called the traveling salesperson problem, and it's well known to be a very hard problem to solve, and so we could imagine trying to solve it on this map. Easier problems to solve on this map, of course, are, say I'm in Olympia and I want to drive to Washington, D.C. What path should I take? That's the shortest. That's a much easier problem to take or to solve. Another problem here, and well, this is the same kind of map, it's a transportation map. But one of the reasons why I've posted this map, you might recognize this looks like a flight map. Okay, a map of where you could fly to. It looks like maybe for an American airline, something like that, where it shows all the destinations you can fly directly to from, North American sources or starting locations. Now, the reason I've put this on there is that the two types of transportation graphs that we have here, that usually we label the edges, the connections between our cities or our stations here, with some value, a number usually, and that number usually represents one of two things if we're doing sort of the Google Map problems. The standard obvious thing to label it with, at least on the road map, is distance. How many miles or kilometers are you going to be traveling to get from one city to the other? However, again, if you're actually doing the Google Maps problem, if you're actually sitting right now in your car and you're staring at Google Maps, hopefully you're not doing that. But if you were, then Google Maps is at the moment probably reporting how long it's going to take you to get there, not how many miles you need to travel. It's probably there too. But really what it's probably telling you is how many minutes it's going to take you to get there, because that's usually what we're interested in. And in fact, if we're actually sitting there trying to plan a trip, if one trip is 20 kilometers, the other one is 50, but the 20-kilometer trip has a lot of traffic on it, it's going to take me an hour, and the 50-kilometer trip is going to take me half an hour, something like that, then I'd rather take the shorter one. Usually that's the idea. Well, how does it work with flight maps? If we use distance or time here, yes, we probably still use time. If I sit down and I'm planning a trip, if it says it's going to take me 27 hours to get from, Seattle to Montana, I'm going to say, where are you routing me through? Are you flying me over to China and back just to get across the state? No, hopefully not. So time is a consideration, but more often than not, the first thing we're looking for is cheap. It's cheapness, okay? And at least me, I'm cheap. So I want to find an affordable flight, and I balance the two. Usually those are opposite kinds of things. The 27-hour flight is the cheapest one because you fly around in circles, but the straight one, the flight that gets you there as quick as possible with no stops, is usually the more expensive one. Not always the most expensive one. But what that means is it gives us an interesting scenario. A scenario that doesn't usually work in normal maps. And in a normal map, the geometry on the map, because the geometry is on a two-dimensional surface, at least we abstract that, the geometry follows normal geometry rules, and there's one expected rule in geometry called the triangle inequality, which can be interpreted a couple different ways. But if you have a triangle, it says the sum of two sides must be greater than or equal to the sum of the third side. It's only equal to if the triangle is actually just a flat line, right? But otherwise the sum of two sides has to be greater than the sum of the other side, which what that sort of means is, say you have three cities here, Helena, Salt Lake City, and Cheyenne, and say you want to go from one, so driving from Helena to Salt Lake City should be shorter than driving through some in-between city. So driving to Cheyenne and then to Salt Lake City, unless it's right on the same route, like we were saying. Okay, and so that triangle inequality, we usually expect that to be true for most of our nodes in a transportation network. But when we start switching to a flight network, where we start labeling with prices instead of distance or time, we can actually get some bizarre situations. And it's very common to have the flight that sort of takes longer to be cheaper than the flight that is shorter. And so as a result, trying to find the cheapest flight, we might actually have to use different algorithms. An algorithm that relies on the triangle inequality can make simplifying assumptions like this. If I'm in Olympia and I'm trying to drive to Washington, D.C., I should go east, not west. But in a flight map, that might not be true. If I want to go from Olympia to Washington, D.C. and it be as cheap as possible, there might be a flight that goes west and then comes back east that is cheaper than starting out by going east. So as a result, we might have to rely on different algorithms to solve that problem if certain assumptions about our graph are violated. And as we get to those algorithms, I'll talk more about them. Okay, I wanted to finish sort of our exploration of what kinds of networks there are out in the world with a couple of biological networks. And part of my reason for that is, well, this is my area of interest and curiosity. I do research in an area called artificial life, and networks show up all over the place in artificial life. One area that you might already have heard a lot about are neural networks. So this is meant to be a depiction of a brain. So our brains are, at least our current understanding of the brain and the way we try and scientifically explain what happens in the brain, is that the brain is a network of neurons. A neuron is a special kind of cell that can be connected to other neurons through, again, other special kinds of cells. And that network forms our brain, and there are billions of such neurons and trillions of such connections. And those somehow, because there's still a little mystery and magic to it, but we're starting to understand it better and better, but somehow that connection of all those simple little tiny cells creates really the wonderful computer that we have in our brain that allows us to do all the amazing things that humans can do, which is still largely unexplainable. But we as scientists and engineers have taken what little we do understand about the brain, and we've built what we call artificial neural networks, which are networks of artificial little tiny computers that are meant to replace or represent, rather, the simple computers that are neurons. And then we wire them together in interesting ways to do some pretty amazing things. In fact, probably the most amazing thing that we've been able to do, we haven't really been able to simulate a whole brain with a neural network yet, but we've gotten pretty good at building an artificial sort of visual cortex, is what I might call it. Again, I'm not really a neurologist, so I don't know if I'm mentioning the brain parts exactly right, but the part of our brain that controls vision, we've really got some really good artificial neural networks that are getting good at vision. And in fact, we've gotten so good at them that we use them inside larger intelligent things that, say, drive cars. Our self-driving cars use some of these neural networks that help it with its vision. And if you've been following this a little bit for the last couple of years, more like the last decade, about 10 years ago, image classification was a very challenging thing to do, and in fact it's sort of the underlying basis behind these CAPTCHAs that you might have encountered online. These CAPTCHAs are these tools that are supposed to prove that you're not a robot, right? And especially in the good old days, and still today, but they're upgraded a little bit, but in the good old days, they would just give you some pictures and they would say, click on all the cats. Because the idea was that it was really hard to build a neural network or any other artificial intelligence device to do image classification, to pick out cats from dogs, or cats from horses, or cats from lampposts for that matter. But one of the reasons they were asking us to do that is we were sort of secretly telling robots everywhere, this is a cat, this is a lamppost, this is a fire hydrant, and through that time, as our neural networks got more and more powerful, our artificial neural networks, they learned, they were trained that these are cats, these are dogs, and we've actually got to the point now, especially that we've added some deep neural networks, deep learning onto these neural networks, that we now have fairly good image classifiers that can look at an image, a novel image, a new image it hasn't seen before, and said, that's a cat, that's a human being, that's riding a bike, something like that. And so we've actually, what that means is robots are getting better at tricking themselves into saying they're not robots. But we've now got to the point where if you're running on CAPTCHAs today, the CAPTCHA that you've probably encountered asks you, what's a stop sign? What's a traffic light? What's a car? What's a bus? And these ones are really to help us train those neural networks that are out there driving cars. And it's important that they know what a bus is, what a pedestrian is, so that they don't cause accidents, of course. Okay? So again, this is just sort of an exploration of how we've start with a network-based understanding of biology, our brain, use that to come up with a network-based engineering project, a neural network, an artificial neural network, even though that artificial neural network is not really a brain. We don't know enough about the brain yet to model it exactly, but we've just made sort of like a rough child's copy of the brain, and even that is fairly interesting, fairly powerful. And remember the idea I mentioned earlier about the robustness of a network when we delete out part of the World Wide Web, for instance. Well, the same is actually true of the brain. I don't recommend doing this, but if you have some brain injuries, there are you can have brain injuries, and it's actually quite remarkable that the human brain, in particular, but the whole human body, can recover from some fairly traumatic brain injuries. Think for a second what would happen if you took a nail and put it through your CPU of your computer, or the CPU of your phone. Chances are you're going to have about 0% functionality when you take that nail out. But again, don't try this at home. If you put a nail into your brain, you could die, of course. That's why I say don't try it at home. But there have been people who have had nails stuck in their brain before that have recovered. I'm not going to say fully recovered, because that's not true, but the brain was robust enough to still maintain enough function to say keep the body alive and keep the human beings conscious and able to perform, regular sort of human being tasks. A very well-known and sort of popular case where this occurred. It happened long enough ago that privacy protections weren't in place, so we actually know the name of the individual. His name was Phineas Gage. He was a railroad worker who suffered a traumatic accident where he got a railroad spike, which is basically a giant nail, stuffed into his brain. And he survived. And he's quite famous because afterwards a lot of psychologists and the neurologists at the time and so on wanted to study him and why, how he survived and what effects this traumatic injury had on his ability to operate. And he definitely had, his personality changed, a whole lot of things changed about him, but for instance he could still speak and talk to people and so on. And the realm of sort of psychology, the psychology of traumatic brain injuries is a very remarkable area to study, which just as an artificial intelligence and artificial life researcher myself, I've sort of just tangentially taken a skim of them in the past, and there's just a wide variety of interesting tales of people who've had different kinds of brain injuries, and as a result have interesting kinds of different ways they experience life And again, the point of this is that the brain is a fairly robust device, that even the loss of some of the brain cells means we can still function at fairly high levels of functionality. Okay, what else do I have here? This network might look a little bit more confusing as well, but the things in this network, the sort of large chunks here, colorful little chunks, are genes, and then the connections between them are different kinds of connections that genes can have on one another. Now, if you don't know very much about genetics, that's fine. But if you are sort of a computer scientist, or you like learning about computer science topics, then genetics is not really too far away. Biology, I always used to think, was sort of squishy, and you had to, there's animals involved, and you had to take blood samples and stuff. But if you get down to the actual the workings of the biological units, the genes, it's really sort of computational in its nature. And so I like to think of genes as just sort of switches that are on-off. That's a little simplistic, but let's just think of them as sort of on-off. And then what happens is when a particular gene turns on, it can have an effect on other genes. It might try and turn another gene on or turn another gene off. And so what you can get is sort of this really interesting cascade of behavior where one gene turns on, it turns on two other genes, which turn off a fourth gene, which turn on another gene, which go back and turn off the original gene, in sort of some kind of weird network like this. And this is what we call a genetic network. Now, genetic networks are really interesting because usually there's one genetic network that is used to control, say, one biological activity, maybe the digestion of a particular type of food source. And so when that food source is introduced, maybe one of your genes turns on and says, hey, cheese is here, turn on the cheese network. All right, it starts producing the enzymes and so on that it uses to digest the cheese. Or whatever other biological function it might be, grow hair or so on. And so we've been studying these genetic networks, biologists, as well as computer scientists, to help them with the computational components, so that we can have more and more control over the genetic life of ourselves and the genetic life of any of the organisms that we use in our life, like our food stuff or our labor animals. So these types of genetic control systems are, again, like the brain, something we're still trying to learn more about. The Human Genome Project was about mapping this, finding out what the human genetic network looks like. Now, of course, all we've done is got a big map of this giant network. Still a lot of question marks about what it does, just like the brain. We can go look at all the neurons where they are, but we still just don't really know what they all do. But both of these sciences, neurobiology, genetics, are really being helped and fueled by all the computational tools that are being brought to bear. So prior to, say, the 90s, where modern computing really kicked off with the internet and so on, prior to that, we really didn't have the computational power to study these biological structures in the way we wanted. But now here we are in 2020, where we have a lot of computational power, power on the cloud. We can take really large data sets, throw them on the cloud, let hundreds or thousands of computers compute on them for weeks or months, and come up with really interesting stuff at the end. So that's basically the power of computation is really being brought to bear in biology in the last couple decades. Now, in my study, I mentioned I like to study biology. I study an area called artificial life. I don't as often build neural networks or even genetic networks, although I have built some of those in the past. I like to focus on ecological networks. And an ecological network is a network of usually species or organisms that engage in predation, meaning one species might prey on another. And I like to have sort of maybe a network of such species connections. So maybe there are plants and some herbivores, and then there are omnivores or carnivores that prey on the herbivores. And then often I like to sprinkle in humans in there that just prey on everything as well. And then we can see how these organisms respond to things like, at least this image is depicting environmental isolation. So we might have some area here, there's sort of a corridor that connects them. How do species evolve in this one affect how species evolve over here? This is the kind of study that I like to engage myself in, and these are what we call ecological networks. So again, networks, these ecological networks we might think of as sort of being social networks on organisms other than humans. And so I don't often get out in the real world and study real animals. I, through simulation, create artificial organisms that engage in these kind of behaviors, which we can then use to study these behaviors in the real world. All right, so I think I want to leave it there as sort of an introduction to what kinds of networks you can encounter in the real world. And at this point, I haven't really actually defined what a network is yet. So I do want to sort of step away from the real world, abstract away, put on my computer science and math hat, and build some mathematical definitions that we can work with formally as we go forward. So a graph or a network, as we've been using the term interchangeably, I have defined here, is going to be an ordered pair. So we'll usually give it a name, G. So it's an ordered pair. G is equal to VE, where V is going to be a set of vertices and E is going to be a set of edges. Okay, so here V, I've just got labeled, I say sort of arbitrarily, if we don't know anything else about our graph, we'll just call the vertices V1, V2 up to Vn. For some n vertices, we could have 0 vertices. And then our edge set is going to be a special set. Now here I've got it, V is going to be equal to this, but E is going to be a subset or equal to this. This set here is going to be the set of all possible edges. So let's see how I've defined that. I'm going to say take a U and a V out of the vertex set, so pick 2 out of there, and then put them together in a set of size 2. And we usually call that a pair, or an ordered pair if it was ordered, but in this case, as a set, we know that order does not matter. So it's going to be a set of size 2 where order doesn't matter, and that's because the direction, in this case, we're talking about what's called an undirected graph, where there's basically no arrow on our edge. The edge goes both directions. And so this type of graph that I've got defined here, this is going to be the absolute simplest variety of graph you might define. All it's got is edges and vertices, and the edges are undirected. And so we call this an undirected graph, or an undirected simple graph, if we need to clarify it. But in general, we might just call this a graph. Again, the only focus about the undirected part is there's no direction on our edges. Now over here on the right, I've sort of just given an example graph. I guess I've labeled the vertices not V1 to Vn, but A to N, I guess. So our vertex set we could just say is this, where we've got the name of each vertex in there. And we can imagine, say if we had the map of the United States, then we'd have the name of, say, the cities that were included in that map here. We don't need to always opt for V1 to Vn. But then when we're thinking of graphs sort of abstractly, as we're applying a graph algorithm, maybe we don't know what names are applied to that particular graph. So when we're working on the algorithm, we'll just give them these arbitrary names, V1 up to Vn. Okay, the edge set, as I mentioned, is a subset of all pairs. So that means if we actually wanted to give all possible edges here, it would include AB, AC, AD, AE, but also AF, AG, AH, AI, AJ, AK, AL, AM, and AN. All of those edges would also have to be included in the whole total of all possible edges. But this edge set here is a subset of that, and so it's only picking out which edges actually exist. So AB, AC, AD, AE, those all exist, but AF does not. BE is the next one included. Okay. Now also, because these are set, I mentioned the orders don't matter, so BA is the same as AB. Okay, and so on. So here I've sort of listed them in a conventional order, but we didn't have to. I could have put in here the set BA, and that would have been the same set. Okay, so just noticing here, I've called them vertices in my definition, but in graph theory, there are lots of different names that we might give a vertex or an edge actually. And so I've been calling them nodes pretty much commonly. They're also known as points. If we're talking about state diagrams, we're sometimes calling them states. And then depending on what we're using the graph to depict, we might call them, say, cities or intersections or whatever else these actually represent in the real world. We can start calling them that, and that's one of the reasons why there's sort of a lot of different names that you might see out there. And because graphs are used for different purposes in different disciplines, you might enter a different discipline and you'll see, oh, in this discipline we're calling them states and transitions. In a different one we call them nodes and connections. In this one we call them vertexes and edges. And so depending on what discipline you're in, you're going to want to be comfortable swapping from one notation or jargon to another. So again, we're going to use sort of edge as our normal term, but I've been using connection very commonly. Also links, lines, branches, transitions commonly if we're talking about states. So there's lots of different terms for them. I personally usually default to vertex, edge, node, connection are my two sort of main terms that I like to use when I'm talking about graphs. So if you're listening to me, you'll probably hear those. But if you hear someone else talk about points and lines, well, it's probably not too hard to understand what they're talking about. Okay, so I do have a couple other pieces here that I want to mention about vertices. First of all, in this graph, all of my vertices have an edge connecting them to some other vertex, but that's not necessary. We could put another vertex out here, O, and just leave it unconnected to everything else. However, we often like graphs that have this form where all our nodes are connected to other nodes. And if all our nodes are connected to other nodes in one chunk like this, we'll call that a connected graph. And I'll probably talk a little bit more about that when we look at the terminology related to graphs. But often we'll like a connected graph because often the algorithms that we might want to perform can only be performed on a connected graph. So I'll just maybe give an example. So if you're trying to, say, drive from Seattle to Tokyo, and you want to go on Google Maps and punch it in, well, Google Maps hopefully should tell you that's impossible. And that's because the road map of Japan is isolated from the roadmap of North America. You can't just drive there, you have to take a boat or a plane or some other way because there are no roads that get you there. So that's what we might call disconnected components of, say, the roadmap of the Earth. But more commonly, what we would say is, why are we looking at the roadmap of the Earth? We should just look at the roadmap of whatever continent we're on instead of trying to isolate the entire world. So again, this is something that we might see, but the point of this little comment here is that we don't need to have that connected nature of a graph, even though most of the graphs we end up talking about in the real world are connected graphs. We can always imagine graphs that don't have that nature, that have isolated nodes or just isolated components, a little chunk of nodes, a little island, if you will. We often call them islands when we're talking about graphs for that very reason. Okay, what else can we say? This is mostly just some more terminology. Again, the terminology sort of flows naturally off my lips because I've been using it for a long time, but also it's fairly natural language, so hopefully you pick it up just in context a lot of the time. So, for instance, we call these 2 points here, U and V, the end points. Here that word point is coming in. We don't usually call them the end vertices or the end nodes, we call them the end points, but basically that's just using that term interchangeably. So again, for any edge, there's always going to be 2 vertices in it. An edge can only ever connect 2. You don't have these weird three connecting edges rather, or arbitrary. You could imagine having something like that. But if we want to connect 3 things, we usually stick another node in between them, right? We can think of this node as connecting 5 things if we want. So that's sort of how graphs build structure. Okay. What else? The vertices U and V are joined by the edge. Okay, we could say C is joined to D. Another term that we bring up a lot, we say adjacent to. or at least I use that, and a little less commonly, you might say incident on. Okay, so all the vertices that are incident on A, or all the vertices that are adjacent to A. And in general, all those vertices that I'm now talking about, we might call the neighborhood of A. So that's another term. So it's just more terms than I can sort of fit on one slide, but they all sort of come naturally. So the neighborhood of A, the adjacent, we sometimes call this the adjacent group of vertices. So we might use that as a function. Give me all the vertices adjacent to A. That would be B, C, D, and E, and so on. So again, we use this terminology just to make it easy to talk about different relationships. Now, finally, the way I've defined things here, it's possible that U and V are the same vertex, like V1 to V1. This is what's called, this edge would be U to U, and we usually call this a loop or a self-edge. And the graph I have depicted here does not have any, and that's because a lot of time, in a lot of definitions of graphs, you'll see no self-edges allowed. I personally favor the definition that says, okay, the basic definition permits self-edges. If you don't want self-edges in your graph, you've got a special kind that says no self-edges permitted. Or vice versa, some people out there on the internet will say, no, a graph does not permit self-edges, and if you want self-edges, you have to say they're allowed. So go out there and check. If they're just sort of being ambiguous about it, make sure you sort of investigate. Do they mean with self-edges allowed or without self-edges? And it often is pretty obvious, depending on what you're using the graph for, whether you should allow the self-edges or not. So for instance, our map of the United States doesn't really make sense to say, well, there's a road that goes from Seattle to Seattle that takes 0 miles or something like that. We probably would just say self-edge is not allowed. They don't make sense in this diagram. But in other cases, in state diagrams, where they represent state transitions in some kind of maybe state machine, then certainly self-edges or loops are a very common type of transition where you stay in the same state. So again, depending on what you're using your graph for, you might want to permit your self-edges or not. Okay, so we sort of looked at an undirected graph. Let's take a look at now its sort of companion, a directed graph. You'll notice over here I've added arrows to all of my edges. Okay, and the difference in the definition is really only I've changed the set here from sets of sets to sets of ordered pairs. Now the order matters. U goes to V. V does not go back. So this is telling me the arrow goes in the direction U to V. If the arrow also goes back, in my diagram here, all my arrows only go one direction, but we could have an arrow coming back now. It allows us now to have 2 possible edges between 2 vertices because we now have 2 directions, to and from, we usually call them. Okay, and so if we're talking about a directed graph and we're talking about adjacent to, we also say adjacent from. So H is adjacent to J, but J is adjacent from H. Okay, and so that's just our again, how we use that terminology. Again, I've sort of indicated that down here below by changing these all to ordered pairs, but in a couple cases, so originally I had them in just in alphabetical order by convention, but you'll notice for a couple of them, it looks like here are KJ. That arrow actually goes from K to J instead of from J to K. A lot of them go in alphabetical order, but some of them didn't. So in any case where that happened, I had to turn them around. Okay, so KJ instead of JK. All right, so I think I mentioned the only difference is this direction, and this is captured by changing this to an ordered pair. And I think I captured this, that UV equals VU if we're talking about sets. That's because AB and BA are the same in an undirected graph, but in a directed graph they're not equal, so you could actually have both appearing in your graph. All right, this leads us now to another pair of definitions that I think are helpful here. When we're talking about the size of the graph, it can be a little bit ambiguous. And in fact, I also don't usually use this terminology because I even find this terminology to be a little ambiguous itself, because when someone says the size of the graph, That's ambiguous and often can mean the size of the vertex set or the size of the edge set. But according to the definitions that I've got set up here, the size of the graph refers to the size of the edge set, where we'll say the order of the graph is the size of the vertex set. Now, this is because when we get into analysis, we have to be sensitive to which size are we talking about. If we say n log n, what do we mean? Is that n the size of the vertex set, or is that n the size of the edge set? And that, that's going to depend on it for our algorithm. So I want to be clear here that usually we use n for the size of our vertex set and m for the size of the edge set. We'll call n the order and m the size, although I mentioned the size is ambiguous, so I don't really like that. And often, when I'm using this, if I can, I won't even go to n and m. I might just leave it as size of v and size of e. That makes it very apparent to the reader what we're talking about. Now, I want to scope in and look at the size of e a little bit closer. How big can e be? Okay, so how big can the graph be? And here I'm talking about the size of the edge set. So working with our same definition and using the one note that we had on the previous slide that said a vertex does not need to be part of an edge. So if we ask ourselves what is the minimum number of edges, the actual answer, given no other criteria, is 0. Okay, so we could just have a bunch of points, no edges. Each point is an isolated island. Okay, those types of graphs are not very interesting usually. Usually we want some edges, but for the sake of argument and for the sake of maybe being exhaustive, those are graphs too. Graphs with no edges are graphs too. But I'm more interested in what the maximum size of my graph is. And the maximum size of my graph is actually going to depend on what kind of graph I'm going to have. Now, to do this, I want to just think for each of our cases one at a time. The first two I'm going to consider are undirected graphs. I've got the spoilers here. Sorry about that, but think with me for a second about how we come up with these values. So in an undirected graph, the first one is going to be an undirected graph with no loops. And I want to know how many possible edges I could have. So when I'm counting them, I have to realize that if I count an edge from A to B, I can't count that edge back again. I've already counted it once. So let's start with our first set. Let's say we have n elements, and I have vertex 1. How many vertices can it be connected to? Well, since there are no loops allowed, it can be n minus 1 other vertices. I can't be connected to myself, but I can be connected to v2 up to vn. So the first vertex 1 can be connected to n minus 1 possible vertices. Let's take some notes as we go here. So we said for v minus 1, it's going to take n, or we can make n minus 1 edges. But v2 then could have, well, n minus 2 edges, because we've already counted the edge between v1 to v2 here. So that now v2 could only be connected to v3, v4 up to vn. So if we keep going, v3 then can be connected to n minus 3, and we can see the pattern here, hopefully. The last node, which is the last node, is actually going to be vn minus 1, can be connected to one other, vn, and then vn actually, we've already counted all the connections it can have, so it gets added up to 0. So we could write this sum if we wanted, I equals 0 to n minus 1. I'm going to add it up in this direction, of I. Of course, 0, adding 0 doesn't do anything, so we didn't have to start at 0. We could start at 1 of I. And hopefully we know that this is an arithmetic series, and this is, I usually call this Gauss's sum. The normal expression of this has an n on top, not an n minus 1. But with an n minus 1 on top, our formula is n times n minus 1 over 2, or n squared over 2 minus n over 2. This is important because I want to get to the next step. The next step is, so this was undirected without loops. So now I want to think, what about undirected with loops? Okay, with loops, Well, this is how many edges we have that are not loops. So how many edges are loops? Well, each node could be connected to itself. So I'm going to do a plus n here. So that would be the same calculation, but up to n now instead. And if we know that, so that's the sum, I equals 1 to n of I is n times n plus 1 over 2. And we can see that because if we add n to this value here, we get what? We get this minus half turns into a plus half. We get n squared over 2 plus n over 2. And we see that that's exactly what this is, n squared over 2 plus n over 2. These are the same. These are the same after we added that n on, of course. Okay, so we actually get n more. That's pretty straightforward here. So we can actually use that now. I want to jump to the next one, which is directed with loops. Okay, not without to start, because it's easier to calculate. Let's go to the same one here. Since it's directed, V1 can be connected to itself, so that's 1, plus every other node, so it can actually be connected to n nodes. V2 can be connected to itself and to every other node, and we haven't counted the node, we've only counted the connection from V1 to V2, not from V2 to V1. So we can actually do another n. And we can continue with our n's here. So how many n's are there here? There are n of them. We actually get a straight n squared for directed with loops. So the last one I want to look at then is directed without loops. Well, we already know that there are n possible loops, so it must be n squared minus n. Okay, so we've got our 4 values here. These, remember, represent the maximum number of edges we can have. The interesting thing about them is every single one of them is theta of n squared. Again, n here being the number of vertices, right? So the size of the edge set, at least maximally, can be order n squared, which is what we have in each one. Now here I've got them listed from smallest to largest. All right, and tied to this, then we will call our graph sparse or dense, depending on how many edges it has. Now this isn't a firm line. There's not a firm line that I can draw here and say everything above this is dense and everything below this is sparse. This is sort of a vague line. But if you're close to the minimum number of edges, which is usually 0 giving no other criteria, or about order n if you are what we call connected, then we might call you sparse. If you're on the other side, you're near this order n squared, then you're probably dense, even if you're not exactly n squared. Okay, sort of third kind of graph, if you like, although it's actually can be applied to both undirected and directed, is when we want to add some labels to the graph. And when we want to add labels, more often than not, we want to add labels to the edges, not the nodes. So here I've got a graph with some numerical labels, although when they're numerical, we usually call them weights. Okay, so a labeled graph is just a normal graph, a vertex and an edge set, plus a label function. And a weighted graph, the same thing, except a weighted function. And the only difference is in a label function, we just map from edges to labels. But in the weight function, we map from edges to numbers. And here I've chosen real numbers. Of course, I've got integers or positive integers here. And so weighted graphs are usually used when we want to start doing calculations of shortest path or some other kind of traveling salesperson solutions and so on. So I want to finish this video just talking a little bit about how we could implement a graph. Now, graph implementation, there's not going to be a straightforward standard way to implement it in the same way there might be a straightforward implementation of a binary search tree or a B tree. And one of the main reasons for that is graphs are very general as a data structure, And the purpose that you're using the graph for usually dictates the kinds of things you want to build into your graph. So usually you're gonna look ahead, see what you're using it for, and use that to inform how you build your graph. Now, with that said, there are two very standard ways to implement our graph, and they parallel this two standard ways to implement any data structure that we've looked at in this series of videos. And that is, we can either link our structure together, like a linked list or a tree. Those are commonly linked data structures. Or we can somehow store the data in an underlying array, so like an array list or the standard implementation of a heap or a map. We use an underlying array. So we really have this choice with our graph. Are we going to use a linked structure where we use references, or are we going to use an underlying array to just store something in a predefined order? And those result in two different kinds of implementation that we usually call adjacency lists and adjacency matrix. So the first one here is an adjacency list. This is the implementation as a fairly standard linked structure. So the idea here is we actually have nodes. So our nodes are implemented as some kind of private class node. And inside that node are links to other nodes. And the way we did that in a linked list would just be a reference to a node, or the way we did that in a tree would be maybe a couple references to nodes, left child, right child, and so on. But in a graph, this usually becomes a list of adjacent nodes, where we just have a list of all the nodes that we're connected to. Now, in some cases, we actually need to stick data in our edges. In a lot of cases, edges can be abstracted away, like we do in trees. In trees, we don't actually make edge data types. We have node data types that have references to other nodes. The edge is just that reference. It's sort of implicitly there. Well, sometimes we need the edge. Maybe the edge has a weight or a label. And if it does, we might need to make a little inner class called an edge now too. And if we do, then usually the adjacency list is actually a list of edges, but those edges themselves contain the two node endpoints. So I can ask the edge, what do you connect me to? I connect you to this other endpoint. Again, adjacency lists can be used for all kinds of graphs, but they tend to be a little more efficient when you're using a sparse graph because remember, you might not have all these n squared edges, so you won't actually have n squared references in your adjacency list. I also happen to favor adjacency lists in my implementation when I need to, just because I happen to favor these linked structures. But if you happen to like array-based, then you might like adjacency matrices. So the idea behind an adjacency matrix is that if you were to build a matrix by labeling, all the vertical axis and the horizontal axis with your vertices, then every entry in there would be an entry for every pair of vertices. So every vertex I and j would have exactly one entry in there, but also, one entry for each direction. So you would have one entry for I to j and another entry, the mirror entry, for j to I. Okay, and every entry has a mirror entry except for the diagonal, which are all our loops. Okay, now we could imagine filling in this matrix with information about our edges. The very simplest way we could do this is with Boolean information. Put a 0 there if there's no edge and a 1 there if there is an edge. Okay, but more generally, we could stick the numbers in there if there's edge weights. And so maybe we'll put a number in there for our weight, maybe -1 if there's no edge, if we don't have negative weights. If we do have negative weights, we might put a null in there if there's no weight, if there's no edge. And in general, we could put arbitrary stuff in the matrix if we want to put labels in there, or if our edges need more than just weights and endpoints, we can put other things in there as well. Sometimes the algorithms that we use store other data inside edges or vertices, so we might need extra stuff inside there. If we're using an adjacency matrix and we're using it for an undirected graph, then the graph has to be, or the matrix is symmetric. Or another way of saying that is we sometimes ignore, say, the lower diagonal of the matrix. We only consider the upper diagonal of the matrix, or the upper triangle, I should say. The diagonal of the matrix is for self loops. I think I've already mentioned that. And then adjacency matrices work well if you have a dense graph or a complete graph. A complete graph is where all the edges are there. A dense graph is one where most of the edges are there. You use n-squared storage to store your matrix, of course. So in a sparse graph, that's a lot of extra space that are filled out with nulls or zeros. But in a dense graph, you're using all that space anyway, so an adjacency matrix becomes a very useful way for implementing your graph. Now again, I'm going to mention here that when you want to implement your graph, these are two choices, but these aren't the only choices. Depending on what kind of graph you're implementing, you might have other choices available. For instance, in some cases I implement a graph that's just a grid. And if you have a grid, well, you can usually implement that with a 2D array much easier than you can do that with a list or a matrix. I guess that 2D array is a matrix, it's just I implement it in a different way. It's a 2D matrix of nodes, where those nodes are all of the nodes in my grid. Okay, that way it has sort of implicitly the north, south, east, west links built into it. So I mention that because if you are faced with the choice of how should I implement a graph, the first two tools you should pull out are these two, but the third tool should be, can I design a special purpose graph that's going to be even better for my purpose than one of these implementations? And if there is a way to do that, usually that means being a little more clever, but it usually means saving some time. And so there are, again, sort of other implementations other than these two. But these are the two standard models, so I recommend you sort of study them and try them in your own graph implementations. And I think I do want to cut this video short here. I'll bring up the next video, we'll talk more about some more graph terminology. Well, thanks for watching, and I guess I'll see you in that next video.